I'm going to begin with talking about what I planned to talk about yesterday, and which was just sort of a refresher of some basic facts about random graphs that are going to be important for the course. And probably a lot of you know a lot of what I'm going to say for the first half of today's lecture. And I'm not going to give many proofs, but I'll give a few, mainly because there'll be ones that we'll do sort of more complicated versions of later on, and seeing proofs in simpler contexts before in more complicated ones can be good. So we'll be talking about sort of two main types of random graphs. Erdős-Renyi and random regular. So the Erdős-Renyi random graph is usually denoted GNP, and this is just basically the simplest recipe you could have for a random graph. So you have n vertices, and between each pair of vertices, you connect edges independently with probability p. So for each of the n choose 2 pairs of vertices, you put an edge with probability p. Now, if p is fixed, then the average degree will be about n times p. You'll get a very dense graph. I want to think about things in the context of sparse graphs. So we're always going to be looking at the case where p is scales like d over n. So the average degree is d. We can say more about what the degree of a vertex v is. It's each one has n minus 1 possible neighbors it can connect to, each with probability d over n. So asymptotically, this is a Poisson random variable with mean d. So in particular, it's not necessarily regular. Some fraction, or like a e to the minus d fraction of vertices, will be have degree 0. They'll just be isolated. But many, and the typical one will have degree d, approximately, if d is big. If I look at the empirical distribution, and I'm probably getting to the lower bound here. Is this about right? Okay. So I could look at the set of vertices and the fraction that have degree I, and this will be asymptotically given by the so I want to say that this converges in probability to the probability of a Poisson. Factorial. So, I mean, how would you show that? Well, the degrees are not completely independent, because, if I take two vertices, whether they have an edge they have an edge, share an edge, so there's some dependence between a pair of vertices. So it's not like these degrees are completely independent. But on the other hand, they're very close to being independent. So let me say I took just a sample of the vertices. So let's say V1 to VR was the first R vertices, and let's say R was n to the 1 n to the 1/3, and I write di prime as the fraction of the is equal to the fraction whose degree is equal to I. So first of all, di and di prime should be close. Why? Well, basically just because if I take some population and sample from it, then the sample mean is close to the population mean. So this is just your sort of basic, say, concentration of sample means you follow from, say, the Azuma-Hofting inequality. And now, if I write A as the event, no edges between vi with I less than or equal to r, well, the probability of A is equal to 1 minus d over n. So we need each of to the r choose 2. R choose 2 is about r to the, or is about n to the 2/3. So this converges to 1. So with high probability, or probability tending to 1, none of these n to the 1/3 vertices we sampled will have any edges between them. And then conditional on A, the dvi are conditionally independent, and the conditional distribution is binomial n minus r. We're conditioning on, no edges between the vertices, but no other information. And because r is much smaller than n, this is still like Poisson d. So conditional on this event A, these are independent, and so the empirical distribution will be very close to the to Poisson. Okay, so okay, so if we look at the set of degrees, their empirical distribution will be very close to Poisson. So we can say things like the fraction of vertices that are isolated of degree 0 is very close to e to the minus d. You could also ask about what's the maximum of the degrees, and this is like log n over log n. This is the same as if you took the maximum of n independent Poisson random variables. So by Markov's inequality, that would give you this is an upper bound. Again, they're not independent, but you can get this a sort of lower bound by just splitting the vertices in half, looking at the n over 2 vertices on the left side, and looking at the maximum number of vertices they have to the right-hand side. And this will, and then these events are independent. There would be binomial n over 2 d over n. We have n over 2 of those events, and the maximum of binomials, n over 2 independent binomials like that, is again like log n over log n. And the fluctuations are really small. It's like this maximum will be concentrated on at most 2 values. So, okay. I had a list of things I wanted to say. Okay, yeah. So that's That's the degrees. That's what we can think of as like the size of a depth one neighborhood of a vertex. What if we wanted to know sort of what the neighborhood of a vertex looks like in a bigger radius? Well, the first thing you can ask about is sort of, are there any cycles? And I mentioned last time that we expect the graph to look locally tree-like. We don't expect many cycles. So if I let ck be the number of cycles of length k, this is something that we can compute its expected value because, well, I can calculate the number of ways of constructing a cycle in the graph. Well, I have to choose k vertices in some order. So n for the first vertex, n minus 1 for the second, to n minus k plus 1 for the last one. So this is the number of sort of ordered k tuples of vertices. But that's sort of overcounting because in a cycle, it doesn't really matter where I start. So I should divide this by k. And it also doesn't matter if I go clockwise or anti-clockwise. So there's also a factor of 2. And then I can ask, what's the probability of seeing each of these edges? Well, that's d over n to the k. And now when n is big, this first term is like n to the k. So these will cancel out. And it will just converge to d to the k over 2k. So if d is less than 1, we're getting fewer and fewer large cycles. And if d is bigger than 1, there's more and more. But also the point is that the number of cycles is just order 1. So as n the number of vertices is tending to infinity, the number of cycles you expect to see is staying constant. So if you take a typical vertex, you don't expect to see it, you don't expect it to be in any cycles at all, or even close to any cycles. So this is the expected value. You could ask about what is the distribution of the number of cycles. Well, the first guess you should make, which is right, is that it should be Poisson, because these are like rare events. They're sort of different cycles are sort of essentially independent of each other, and so Poisson is usually the law of lots of the number of rare events that happen. Okay. So, and a Poisson distribution has exponential degree, exponential tails. So you could prove it by showing that the moments converge to the moments of a Poisson random variable. So calculating expected value of zk to the L. Now, a slightly easier calculation than working out the moment is sort of the falling factorial. So working out a different polynomial. And this corresponds to what's the expected number of L distinct cycles in the graph. Not distinct meaning different cycles, but they could potentially be overlapping. Okay, so we could work out the expected number of this in a similar way, but there's sort of more possibilities. So let me just assume that L is 2. So one particular pattern of these cycles would be to just have 2 disjoint cycles. And then if we went through the same calculation, we'd get n minus 1, n minus kl plus 1 over 2k to the L for the number of ways of choosing these 2 different cycles, dn to the k times L. But there's some other possibilities too. It could be that
When you say distinct, you mean edge distinct or vertex?
vertex. Yeah. Well, here I meant, okay, in terms of what this means, I meant, yeah, distinct as in just not the same cycle. But yeah, for this, I mean, yeah, vertex distinct. But my cycles could share a vertex, or they could, you know, share an edge, or something more complicated than that. Or maybe with 4 cycles, maybe you can't have something more complicated than that. But what you can check, and I'm not going to do it, if you look at sort of the number of vertices in any of these other patterns minus the number of edges, this is always going to be less than 0. However you sort of piece them together, unless they're just completely distinct. So then when you write down the number of ways of doing this, you'll get something here that's like n to the number of vertices, and then you'll multiply it by d over n to the number of edges in the picture. And so we'll just get something that's order 1 over n. So this distinct vertex distinct cycles is the main order term. And so asymptotically we'll get d to the k over 2l over 2k to the l. And this is the same as what you'd get if ck was a Poisson with mean d over 2k, or d to the k over 2k. So this sort of verifies that the expected value of ck to the L is asymptotically the same as the expected value of a Poisson with mean d to the k over 2k to the L, and therefore that we have convergence in distribution. So this is just for the number of k cycles, but you could do the same sort of argument and show joint convergence for the number of cycles and show that they converge to independent Poisson random variables. So the cycles are rare, they're basically independent of each other, and they're asymptotically independent Poissons. Okay, and these are sort of the only deviations from the graph being locally tree-like. But these sort of deviations, these rare cycles, are going to come up because they'll slightly affect the number of colorings you have in the graph. If I look at the, let's say I'm counting colorings of the graph, and I want say, is the number of colorings close to its expected value? If the degree is not too big, it will be, except there'll be some correction for the number of cycles of different lengths you have. We'll see, I'll talk about that a bit later. Okay, and there's the eraser. Okay, so the last thing I want to talk about with Erdős-Renyi random graphs is sort of what they look like locally. And we can talk about this in terms of the local weak limit, also the Benjamin Mini-Schramm limit, which is to say we take a sequence of graphs Gn, and this will converge in the sense of local weak convergence to a random pair, a random rooted graph. So G will be some random graph, rho will be some distinguished vertex in it, and we'll say it has this local weak convergence if for all R, for all G, and UN is a uniform vertex in Gn, that if we take, so a ball centered around UN of radius R in the graph Gn. So we have our graph, we're picking a vertex at random, and we're exploring some ball of radius R around it. And we ask the probability that this is equal to some fixed graph, and we want this to converge to the probability that our sort of limit random graph is equal to that same fixed graph. So we're asking something about the convergence of the distribution of local neighborhoods. If R equals 1, this is just a statement about convergence of degree distributions. So we showed that. So we already showed that essentially the distribution is converging to a Poisson. Okay, so just to give an example, if my graph Gn was an n by n block of the grid, this would converge in the local weak convergence sense to Z2. So if you pick a random vertex and look at its local neighborhood, well, most of the vertices are not going to be on the boundary of this grid. They're going to be in the middle. So their local neighborhood will just look like, they'll just think that they're in some very infinite plane, at least if they just look up to radius R. On the other hand, suppose I took a binary tree of, let's say, depth n. What would its local weak limit be? Well, the first thing you might guess is the infinite binary tree. But this is actually not the case, because if I sample a random vertex in this sort of n-level tree, what's the most likely type of vertex to get? Well, it's a leaf. There's a lot more leaves than vertices close to the root. So your typical local neighborhood will look like the local neighborhood of a leaf. And so the local weak limit is actually what's called the canopy tree. And basically it's a single infinite path going up to infinity. And then hanging off the vertices on the path, you have a depth 1 tree, a depth 2 tree, and a depth 3 tree, and so on. And then the root is chosen along this infinite path with sort of probability a half of being the first one, and a quarter, an eighth, and so on, corresponding to the probability of what level vertex you picked here. Okay, so that's just a couple of examples of local weak limits. What local weak limit do we get for Erdős-Renyi random graphs? Any questions about this so far, by the way? Yeah.
Should we think of G as random,
Here? Or,
The limit object.
yes. Yeah, so it could be a deterministic graph. So actually, I guess in the two examples I've given, the graph is deterministic. In the second example, the graph was deterministic, but the root vertex was random. But as we'll see in the Erdős-Renyi context, the graph will be random there. Yeah.
What was the intuition behind the disjoint cycles contributing to the product of cycles of different lengths, number of cycles of different lengths?
The intuition, I guess, would be that so I can, there are lots of possible cycles in the graph. Most of them don't occur, just on average a constant number. But if I have, if I have two cycles with disjoint sets of vertices, then whether they're present is independent, and that essentially that's the main contribution. So it's lots of sort of independent lottery tickets, and just a few of them come up, and that will be sort of asymptotically Poisson. Whereas the probability of having two cycles that sort of intersect each other being present will be much smaller, because there's sort of less ways of choosing the vertices. Yeah. Now it may be that if they overlap in an edge, there's also fewer edges that need to be present, but the fewer number of vertices isn't enough to sort of compensate for that. Good. Any other question? Yeah.
So here it's a bit surprising that you get the canopy tree. That's not the first thing you would think about. So maybe if you change the backlight to any uniform, is it interesting to look at other like variations of this, where it's maybe deterministic?
Yeah. So I mean.
Like if you always took the root, for example.
Yeah. So I mean. You can certainly, this definition is sort of like weak convergence in sort of some local limit of, in some sort of metric on rooted graphs, where I sort of, I can think of, if I have two graphs, G row and G prime rho prime, I could look at the distance. I could sort of define the distance between them as, let's say, 2 to the minus the maximum over R, such that the ball of radius R sort of agree with each other, so have the same are isomorphic. So this is sort of saying, I take my two graphs, I see how big a radius around them are they isomorphic, and takes a sort of 2 to the minus that as the distance. If they're just isomorphic as graphs, then we'll get 0, because it was true for every R. So this is a metric on rooted graphs, and this is sort of weak convergence in the sense of this this metric. So then it does make sense to talk about sort of a limit of a deterministic sequence of rooted graphs, and in that sense, if I took this n-level tree and always picked the root, then it would converge to the infinite tree. And you could maybe imagine, some weighting of vertices that wasn't uniform, that might be interesting to look at in particular examples. But I think for our purposes, we'll be basically looking at the uniform case. But yeah, but basically it's meant to be a notion of what does the distribution of some local neighborhood look like, and then it sort of just depends on what distribution of vertices you want to look at the local neighborhood around. And so yeah, you could take a non-uniform distribution for that. Good. Any other questions? Okay. So the Erdős-Renyi random graph is going to converge in the sense of local weak convergence to a Galton-Watson branching process with Poisson D offspring distribution. So this means the root is Poisson with mean D, and then each child has an independent number of children that's also Poisson with mean D, and you keep going with that. So it's an infinite tree. And the way you could prove this is basically just by coupling the distributions. So the root we know has degree binomial n-1 d over n, so it's asymptotically Poisson. And then, okay, suppose that it had, let's do a breadth first search of the vertices starting from the root. Well, given that it had 3 children here, ask, well, what's the distribution of this one, or the number of children that it has that are ones that we haven't already explored? Well, it will be binomial n-4 d over n, conditional on the root having degree 3. But n-4 is also very close to n. So this is also asymptotically Poisson. And maybe this had 2 children, then this next one would be binomial n-6 d over n. And so we could couple the sort of exploration process of in the Erdős-Renyi random graph with the Poisson-Galton-Watson tree, and until the point at which we've sort of explored a lot of vertices here, each new vertex, the number that we'll look at will be binomial n minus something small d over n, and those will all be asymptotically very close to Poisson. Yeah.
So I see from the definition where you get the Galton-Watson tree.
Yeah.
It would look more natural to get the Poisson Galton-Watson forest rather, because you have all these little components. So this is really because you have a local.
Yeah. So that's right. So it's so the sense of convergence is what does the neighborhood look like around some particular vertex? Yeah. So indeed, if I look at all of the vertices at once, then I'll get a collection of well, trees. Not necessarily all trees, though. But yeah. But for this, for this notion of convergence, I really just want to focus around sort of one particular random vertex, and then what you see is a tree. Although now, of course, there's some probability that when we explore the first R levels, we find some cycle, but the probability of that is tending to 0 because we know there's only order 1 numbers of cycles. So asymptotically, what we'll see is a tree. Good. Any questions about that? Okay. Let me say. Okay. So let me just mention a couple of the most famous results about Erdős-Renyi random graphs, which I'm not going to prove, but if you have a Galton-Watson branching process, if D is less than 1, or in fact less than or equal to 1, then the probability that it dies out, so it stops after a finite number of levels, is 1. So on average, the number of vertices in each level will be, in level k, will be d to the k. So if d is less than 1, it's sort of, in expectation, it's going to 0. If d is equal to 1, it's 1 in expectation, but it still dies out almost surely. Whereas if d is greater than 1, then the probability that the branching process survives forever is positive. And it's something that you can calculate. I won't go through there's nice proofs of this in terms of generating functions. I won't go through it. But it's sort of, this behavior is also manifested in the behavior of the random graphs. And so if I take my Erdős-Renyi random graph and look at the, let's say, the connected components, and let's say that they're ordered, that their sizes are W1 greater equal to W2. So these are so I take all the vertices in the graphs, I take the size of the components and put them in order. Then if D is less than 1, then the size of the biggest component is less than or equal to a constant log n. This is with high probability. And this is because, any vertex you start with, the graph will sort of die out. When I start exploring from some vertex, it will sort of die out quickly. And the biggest thing you'll see will be of size log n. So in this case, if I look at the connection, or the collection of different components we get, it will indeed be sort of like a forest of lots of trees. There'll be a few cycles. So some of the trees will not be trees, but they'll be like a unicyclic component. So it's like a cycle with some edges coming off it, but there'll only be order 1 of these. But mostly trees, and most of them will be of size order 1. And the distribution of the sizes is something that you can work out from the local weak limit. And now if D is greater than 1, on the other hand, there'll be the biggest component will be of linear size. It will, some constant C2 that's strictly between 0 and 1. And so a constant fraction of the vertices will be in one giant component. But all the other components will be subcritical. They'll be less than or equal to log n. So, and in terms of random constraint satisfaction problems, it's this second case that will be interesting. In the first case, where everything or almost everything is in a tree, it's pretty easy to answer all the kind of questions you might want to answer, like, if you have a tree, there's always a way to color the vertices. You just start with the root being blue, and then the next level being something other than blue, like red, and then the next level is blue, and so on. So you can always find colorings. It's easy to work out how many colorings there are. And this is true for all the other random constraint satisfaction problems that we talked about. This supercritical case where there's a giant component will be the more interesting setting for us. And so we have one very big component and then a lot of other small trees. And now in this big component, there are no small cycles, but there are going to be lots of big cycles. But you have to go to length sort of log n in order to find those large cycles. this is actually quite a well-connected graph. So locally it looks like a tree, but globally it has sort of good expansion properties, and it's sort of the presence of these very sort of long-range cycles that will sort of, in a sense, determine whether or not there are ways of coloring the graph. So it won't be enough. When D is large, it's not enough to just look at the local neighborhood. You need the effect coming from sort of very far away. And we'll try and understand that. Yeah.
Maybe a stupid question. So what about like D equals to 1?
D equals 1 is very interesting from the random graph point of view. In this case, the largest component is of size n to the 2/3. The second largest component is also a size n to the 2/3, and actually there's a way of writing down sort of like if we took the largest few components, divided them all by n to the 2/3, there's a sort of these converge to a joint distribution, which is something that you can write down in terms of excursions of some Brownian motion with drift. And so that's a very interesting sort of random graph, or from the random graph point of view. It's not as interesting from the random constraint satisfaction problem point of view, because although the biggest components are much bigger than in the sort of subcritical D less than 1 case, they're still trees with sort of order 1 number of edges extra, so that it's like, so you would get sort of the biggest components would look like a tree with about n to the 2/3 number of vertices. This would be something like Aldis's continuum random graph or continuum random tree sort of distribution, but then plus order 1 number of cycles. But because it's such a big tree, adding in a few cycles doesn't really change the colorings or other random constraint satisfaction problems on it. So it would still behave a lot like the first case, but yeah. So but yeah, thanks for asking about that. Any other questions? Okay, so that was a very brief introduction to the Erdős-Renyi random graph. The other model of random graphs I want to talk about is
Sorry.
oh
Just before.
yeah.
I'm not understanding this moment. So why long cycles have more influence in satisfaction problems rather than small cycles?
Okay. Yeah, that's a good question.
Because the only difference between 2 and 3 is the length of the cycles, right? Because the formula is CK is equal to DK over 2K. So smaller cycles are more probable, right?
Okay, so the number of cycles was like d to the k over 2k. Yeah. So when d is bigger than 1, there's a lot of long cycles. Once k is logarithmic, this starts being of sort of order n. So your typical vertex will start being in sort of a lot of long cycles. Yeah, so it's, I mean, there are very few short cycles, so that there won't be enough of them to sort of impact things much. It will be more a question of, if I have a vertex v, it's connected to some other neighbors. And, well, okay, so suppose U1, U2, up to UD. Suppose we're adding in a vertex, and these are all part of the graph. So I want to understand sort of when I add in one extra vertex, how does that affect the number of colorings in the graph, say, or the number of solutions to my CSP? Well, it will depend if I look at sort of a random coloring in this graph without the vertex U. It will depend on sort of what is the joint distribution of the colors on these, vertices that are going to neighbor you. And they're going to be, and these are sort of randomly chosen vertices in the graph, so they'll tend to be very far apart. So in the simple case, in the replica symmetric case that I talked about yesterday, these will be essentially independent of each other. But when one gets into the replica symmetry breaking case, these will start to not be independent. There'll be some, their joint distribution will be a mixture of product measures, but in general, a mixture of product measures is not a product measure. And the reason why, so these are a long way away from each other until I've connected them to U. So their local neighborhoods are disjoint. It's only the sort of long paths that are joining them up that are causing some dependence between the, whether this one being blue affecting the probability of this one being blue. And so it's sort of those long range interactions that will really affect the process. Yeah, but hopefully this will be something that becomes clearer as we go on. Yeah, good. Any other questions? Okay. So the other model will be a random deregular graph. And here we have a graph again on n vertices. And we just choose uniformly from all deregular graphs. Okay. So deregular meaning all of the degrees of D. So this is sort of a much less constructive definition of how to build one of these graphs, because it just tells you, look at all of the graphs that are deregular and pick one of those at random. It doesn't, but if I tell you, okay, these edges are in my graph, it doesn't sort of lend itself very well to saying, okay, well, what's the probability that this other edge is in the graph? The edges are no longer independent because, well, if one vertex has, if I tell you one vertex has D neighbors, you know that it's not connected to any other ones. So that's sort of a complication. So to deal with this, Bolabash introduced what's called the configuration model. Okay, and what's the configuration model? Well, this is sort of a recipe for building one of these deregular graphs, which is, imagine we have this graph and I just sort of take a pair of scissors and I cut each of the edges in half. So each vertex has D half edges sort of dangling off it. So we have our n vertices. and each of them have sort of half an edge, d lots of half an edge hanging off them. And then, okay, if I want to, reconstruct the graph, I need to match up these half edges. So I take just a uniform matching of the half edges. From this one. Okay. And then I make my graph by saying that, U is connected to V if there's a half edge, if they have half edges matched. Okay, so this is in this definition, there's a lot more sort of independence present, because if I tell you what some of the half edges, where some of the half edges are matched, the remaining ones are still uniformly random. Okay, so that's the good side. The bad side is that the graph that we get may not be a graph at all. It's more generally a multi-graph, and that's because of some things can go wrong. Like this, in this vertex, two of its half edges got matched together. So we have an edge going from the vertex to itself. So this is called a self-loop. And then, okay, these two vertices have a pair of half edges connected to each other. So it's connected twice by edges. So you can have multiple edges as well. Okay. So whereas we really want a simple graph, meaning no self-loops or multiple edges. And so the useful theorem will be that conditional on being a simple graph, then it's a random deregular graph. So conditional on simple, then the configuration model is a random deregular graph. So on the event that none of these happen, then we just get a uniformly chosen deregular graph. And basically the reason for that is just if I don't have any of these self-loops or multiple edges, sort of every deregular graph can be realized the same number of ways in terms of matching half edges together. So they'll each be equally likely. Yeah.
So say you have only like 3 vertices, and then now you have like 9 half edges. So there'll be like 1 half edge.
Yes. So if you want a deregular graph with n vertices, then you need d times n to be even. Otherwise, there's no way to make it add up. So either d should be even or n should be even. But that's true. If we, matching up an odd number of half edges wouldn't work, as you say. Yeah. Okay. Yeah, because the total number of edges in a deregular graph on n vertices will be dn over 2. Okay. So why is the configuration model more useful? Well, imagine we wanted to, again, calculate ck, the number of cycles.
Alan, can you comment on what is the probability that it is simple?
I will comment on that, yes. And yeah, so I'm getting to that. But it will be a constant probability. Yeah. Yeah, so if I wanted, let's say, the expected number of 3 cycles, not so easy to see how you would do that in a random deregular graph. You know, if I tell you that these 2 edges are present, what's the probability that this third one is present? I'm not sure how you would calculate that without going through the configuration model. On the configuration model, on the other hand, well, again, we can pick the vertices. And the starting point and the direction around them. So let's say we have these ones, but then we also need to pick sort of the half edges that get matched. So the first one, there's sort of as we go around the cycle, we'll have sort of D choices for the outgoing half edge, and D-1 for the choices for the incoming one. So we'll get a D to the K, D-1 to the K for choosing the half edges that we want to get matched up. And then we've got to ask, okay, so now if I want to connect particular half edges, so match up these ones and these ones and these ones, what's the probability of that? Well, okay, if I take this first half edge here, so far, I haven't matched anything up, so it could be connected to any of the dn-1 other half edges with equal probability. And then once these are connected, then this next half edge, what's the probability, the conditional probability then that it gets matched up with this one? Well, okay, it doesn't get matched up with itself or these other 2 that have already been matched up. So there's dn-3 remaining possibilities, and it keeps going like that. And you get dn minus 2k plus 1 for the last one. Okay, but all of these are about d times n. So the d times n will cancel out with the n to the k here and the d to the k here. So asymptotically, we'll get d-1 to the k over 2k. Now for the Erdős-Renyi random graph, we looked at cycles of length 3 or more. You can't have cycles of length 1 or 2, but in the configuration model, you can. And the number of self loops is just the number of length 1 cycles, and the number of multiple edges is the number of length 2 cycles. Okay. Now we could go through the same sort of calculation as we did last time and look at, the moments of the number of cycles in the configuration model, and we will get that these converge jointly to Poisson random variables with mean d-1 to the k over 2k, independent. So if we want so Ramon's question, what is the probability of being simple? It's the same as the probability of having no cycles of length 1 or 2, which is the same as a Poisson, the first 2 of these Poisson random variables being 0. So e to the minus d-1 over 2 squared over 4. and this is just a number between 0 and 1. So it's greater than 0. So fortunately, this event on the, of being simple is not so rare. It has a constant probability. And so, in particular, if AN is a sequence of events on graphs, and the probability under the configuration model of AN tends to 0, then the same thing is true under the random deregular graph. And the proof of this is just by writing conditional probabilities. The probability of the event under the deregular graph is the probability under the configuration model, given that it's simple, which is the probability under the configuration model that of AN and simple over probability of being simple. And this, in the numerator, well, AN has probability tending to 0, so AN and simple has probability tending to 0. And in the denominator, the probability of being simple is tending to a constant, so this tends to 0. So what it means is that if we can prove things under the configuration model with high probability, with probability tending to 1, then that will also hold in the random deregular case. And because of the extra independence in the configuration model, that's often a lot easier. So how am I doing for time? Yeah, I'm definitely going to keep falling off this, but okay. So
just out of curiosity, the number of cycles of vector 3 in the random deregular graph.
Yeah. No, it will. I mean,
because that's not guaranteed by this, because that's a constant probability type of behavior.
That's right. Yeah, but asymptotically we have the number of So events that have a constant probability may not be, have the same constant probability under the configuration model or the random deregular model. In the case of, the number of 3 cycles, say, we have asymptotically the number of 1, 2, and 3 cycles are independent in the configuration model. So if I condition on the number of 1 and 2 cycles being 0, then the number of 3 cycles is still Poisson. So in that example, but if I but for other things like I don't know, if I looked at, say, the number of independent sets on the configuration model, and compared that and divided by it and sort of normalized that would have a different limiting distribution as the number of independent sets under the random deregular model. So you do have to be a bit careful about these things, yeah. Yeah.
So is this property used for numerical simulation as well? Because if you want to simulate, like to draw a sample from a simple use the configuration, because it looks inefficient for large D.
Indeed, yeah. For yeah. So this is like e to the minus d squared sort of, so for even moderately big D, this is very bad. There are, oh yeah, sorry, the question was sort of, how would you simulate a random deregular graph? So when D is 3, you could just use the configuration model, check if it's simple, and then if it's not simple, sort of do it again, and you won't fail too many times, and so that will be a reasonably efficient algorithm. But if D were 100, say, your success probability would be like e to the minus 100 squared over 4, which is not so good. So are there algorithms that more efficiently sample when D is big? And I think the answer is yes, but I can't really remember how they go.
Because it's really close to zero.
Indeed, yeah. And I mean, there's sort of a lot of work on sort of what happens when you have D as a growing function of n, and
You just need to simulate one, even if it is a trivial one, and then you switch the edges.
that's true. Yeah. So there are right. You can do sort of Markov chain sampling for.
You just need one, even if it is trivial, then you start to switch the edges.
Okay. Yeah. No, that's that's a good way to do it. So the suggestion was essentially a Markov chain Monte Carlo. Okay. Yeah. So when for a while there were sort of limits on how big a D this was sort of understood for, but I think in the last few years, sort of even essentially any sort of D, these probabilities are well understood now. Like D growing with n and being like linear in n, say. Okay, good. And
They're understood, but are they the same as what you wrote, or are there now corrections?
there are corrections, yeah. Oh, yeah.
Sorry, I couldn't understand because I was thinking if the difference for D depends on n, and I want to prove that something like an event goes to 0, then I have that as the denominator, which means that then I get the
Indeed.
numerator.
Indeed, this only holds when sort of D is fixed. Yeah, that's a good point. And for the purposes of these lectures, D is going to be fixed, so I won't sort of try and do something more complicated here. But indeed, if D were growing, then one would have to maybe think about something more complicated, or compare the sort of probabilities of these events. Or good. Any other questions? Okay. So I wanted to give one example of how this can be used. So maybe, by the way, I'll write n for, let's say, the number of perfect matchings of n objects. And there are different ways of calculating this. So n should be even here. So it's like n minus 1 times n minus 3 times the 3 times 1. So just a product of all the odd numbers less than n. I can also write it as n factorial over 2 to the n over 2 n over 2 factorial. This is, you can think of this as I'm creating a perfect matching by first just generating a permutation. So, and then I take, so that this gives me a sequence of n over 2 pairs, but I don't care how those pairs are ordered. And I also don't care sort of, you know, the ordering within each of the pairs. So we need to factor out this form. And now if we use Stirling's formula, so n factorial for large n is like square root of 2 pi n e to the minus n to the n, and plug that in here. N over 2, and cancel, oh, and there's a square root of 2 pi n over 2, and cancelled everything out. The square root 2 pi's would cancel out, but we'd still be left with a square root of this 2 from this denominator here. These two are like n to the n over 2. You get n to the n over 2, and e to the minus n over 2. Okay. And so the number of matchings in the graph will be, so we're matching up d times n. So it will be asymptotically like square root 2 d e to the minus 1 n dn over 2. So unlike for the Erdős-Renyi random graph, where we had lots of small components, a constant fraction of the vertices were sort of just isolated, random d-regular graphs are sort of well connected, at least when d is greater than or equal to 3. So, and they're even better connected than that. They're expanders. So let me say that G is a lambda expander, and this is going to be like a vertex expander, I guess. So there's different definitions of expanders in terms of edges or vertices, but let me just write it like this. Because it's d-regular, it won't matter much. So if for all sets S, the number of edges between S and S complement will be greater than or equal to lambda times the minimum of S and S complement. So if I take a set S here and it's smaller than size n over 2, the number of edges going out of it will be proportional to its size. Okay, and the theorem, and in particular, this implies that the graph is connected. Because if it was, if it was not connected, I could split the graph into 2 parts with no edges between it. The probability under the d-regular model that G is connected and is a, let's say, 1 over 100 expander. These converge to 1. So, and the first one is implied by the second one, and I should say that this is when d is greater than or equal to 3. When d equals 1, it's obviously not true because random 1 regular graphs are just pairs of, or just a collection of disconnected edges. And when d equals 2, the graphs are just sort of a collection of cycles. And so they'll typically not be connected and definitely won't be an expander. But once you have degree greater than or equal to 3 and local neighborhoods are sort of expanding, then the graph will be an expander. So in the notes, there's the proof of this second one, but to make things easier, let's just do the proof that it's connected. Yeah.
Sorry, it's a very basic question, but do you have natural bounds on lambda? It should be less than d, I guess.
Certainly less than d. I think sort of a lot is known about it, and
What's the 100?
That was just me writing something there so that I was 100% sure was true. Yeah. But yeah, one could definitely do better than this. Yeah, but sort of the idea is that it's a well-connected graph. Yeah, Dylan?
What are the tail bounds like on this?
Okay, yeah, so what's the easiest way for it to be not connected, say? Basically, it will be to have like a clique of size d, which is something that you can sort of calculate the probability of. But let's see how we would prove this in just sort of. So I'm just going to do the connected one, and we're going to do it under the configuration model. And then, if we prove it under the configuration model, then it's also true for the regular. Okay, so imagine we have a set S of size k, and I want to ask what's the probability that there's no edges going between the two. Well, that means that S must be a uniform matching of edges, and S complement must also be a uniform matching of edges. So the probability that there's no edges between S and S complement is so there's the number of matchings of dk things inside S times the number of matchings of d n minus k things inside S complement divided by the total number of ways of matching all of the vertices in the graph. And asymptotically, I can substitute that in. I'll just write order 1 for the root 2 factors. And then, okay, so we'll get d e to the minus 1 k to the k. Oh, there should be, sorry. Over 2. All the factors of, because d over k plus dn minus k adds up to dn, all the factors of d and e to the minus 1 cancel out. And we'll get basically k to the k, n minus k, n minus k over n to the n to the power of d. And, okay, this is d over 2, indeed. Yes. And this is going to be roughly like n choose k to the minus d over 2. There's maybe a factor of square root k there as well. But, okay. And then, I'll just finish it off here. And so then the probability that it's not connected is, well, we have to find at least one set S, like this. So sum over size k, the number of choices of S will be n choose k. And then the probability that S is disconnected will be like n choose k to the minus d over 2. So we get essentially n choose k to the 1 minus d over 2, and k, so k up to at most n over 2, and this is something that's summable and tending to 0. So and we see here exactly that we need d to be at least 3 to get a negative exponent there. So this will tend to 0 under the configuration model, and therefore we have the same thing under the regular model as well. And the sort of the biggest sort of error terms would be for the sort of smallest values of k that you can choose. But we'd have, so I think we'd have to take k equals d to be the smallest one that you can, well, okay. Actually, I guess that the errors, actually, if you wanted to compute it exactly on the deregular, like the tail bounds on the deregular case, you would get something different to what you would get in the configuration model case, because in the configuration model, you can have just a single vertex that sort of has all of its half edges matched to it, if it's, say, if d is even. And that's more likely than in the, but you're not allowed to do that in the graph case. In the graph case, the smallest disconnected set you could have would be a clique of size d, and that will be more unlikely. So yeah, this is sort of an example of if we want to sort of study rare events, then we might get sort of different probabilities under the configuration and regular. Okay. And now, so this was for showing that it's connected. If we want to show that it's an expander, then we'd have to sort of choose a certain number of half edges going between S to S complement. So so we'd have to sort of sum over all of the possibilities of the ways of doing that. But if there's not many of these, then it doesn't sort of increase the probability by enough to compensate, and it's a calculation you need to do. But if we're only asking for sort of k over 100, at most k over 100 edges, it just doesn't increase sort of this probability by enough to allow a small number of edges between S and S complement. Okay, so so this was all I wanted to say about sort of random graphs. Any more questions about that? Yeah. Yeah.
And expanders in general, do they seem like random irregular graph or not in general?
So I mean, like an expander doesn't have to be locally tree-like, so it could have lots of cycles in it. But for some things like they do have a lot of properties in common. So in terms of the neighborhoods will expand exponentially. If you have an expander graph, it means that the spectral graph of the spectral gap of a random walk will be bounded away from 0. So mixing times will be fast. Yeah, but it's I mean, but there's a lot of specific properties of that random deregular graphs have are not shared by, say, all expander graphs. Yeah.
Sorry, I don't know if it's a good question, but for example, for the random triangular graph, we use the configuration model, which is a nice, simple algorithm to make it.
Yep.
And for the expander, like, are there also some kind of, I don't know, simple algorithm to create an expander?
So there are, yeah, so this would give you a random algorithm for making an expander. There are explicit ones. There are sort of ones using, like, some of the earliest examples were like using sort of like number theory type stuff. So Lubotsky, Philip, Sarnak had constructions of expanders. There are, yeah. So yeah, and there are other constructions in theoretical computer science that were sort of maybe a bit more algorithmic, that were used to show, let's say you have I give you a graph, and the model of computation is that you only have log n bits of memory, and you want to be able to check, is this graph connected? And this was an open problem for a while, and it was sort of you want to be able to sort of and sort of some, I'm forgetting the details now, but there were some explicit expander constructions that were able to sort of check, is such a graph connected or not in log space.
I recommend, there is a beautiful review article in the bulletin of the AMS by Vidgerson and a bunch of other people about expander graphs. It's really worth reading if you're interested.
Okay.
Maybe ask you the name later if that didn't.
I have to. Avi Vidgerson is one of them, but there's like 4 authors, and I don't remember. But if you in the bulletin of the AMS, it's about expander graphs. It's a review article, and it contains all sorts of interesting information. It's very well written.
Okay. So I'm now down to 2 minutes left. So this is maybe a good time to. Are there?
Yeah. Well, it is known that in some sense, Erdős graphs can also be viewed as an expander with some stuff added on top of it.
That's right. Yeah. Yeah. So. Absolutely. So, Erdős-Renyi random graphs, might seem like they're not expanders because they're not even connected. But if you look at the giant component, well, that's also not an expander because it has sort of like a, a dense part with maybe some like trees, long trees hanging off it. But if I sort of did some surgery and say deleted all the sort of trees hanging off it, and then maybe there's sort of some long paths with a lot of vertices of degree 2 along them, and so I sort of say contract all of these into single edges, so now the resulting graph I have, everything will have degree at least 3. Then actually this resulting graph will be like a configuration model, except rather than starting with 3 regular, so every or deregular, the vertices can have different numbers of half edges, but they're all at least 3. And then with high probability, what we get here will be an expander graph. So so there's sort of like a core of the graph that behaves like an expander, then with sort of stuff hanging off it, and then some of the edges you need to replace with sort of a geometric number of vertices along them. So yeah, and so for instance in random graph, or in random, if I was thinking about random walks, on a, let's say, a random deregular graph, the mixing time is log n, so it mixes very quickly. On an Erdős-Renyi random graph, if you start in the giant component, you could start on sort of some log n length path that's hanging off the giant component. This will take time. Then it will be like a random walk on a path, so that will take about log squared n until you get into the main sort of core of the graph. So the mixing time is like log squared n for that. But if you start from a random vertex, these will be sort of quite atypical. If you start from a typical vertex and look at how long it takes to mix, it will typically be log n. So viewed from a typical, so the sort of parts of the random graph where it's not really expander-like are sort of atypical. And so morally, as you say, it's sort of quite expander-ish, but not matching the formal definition.
So the question I want to ask is, can this, of course I do not know how you will use the expander property for the satisfaction part, but could that also be used, or?
Yes, yeah, so tomorrow I'm going to start talking about what do sort of these random distributions look like on these graphs. So what do spin systems look like on random trees and random graphs, and knowing that the graph is sort of mostly like an expander, indeed can be useful for proving certain properties. Yeah, okay, so now I'm properly out of time, so we should finish off now and have coffee.